This is the instruction and introduction to experiment or lab 2 density of liquids. So for those that don't have the objectives, I know one of my class does, I'm just going to review them pretty quickly. And you would say number 1, 2, determine the density of water, Diet Coke, and Red Coke. Number 2, determine the grams of sugar or carbohydrates in a can of Coke, which by the way will be 355 milliliters. So we're going to determine the densities of regular and Diet Coke and somehow through that data calculate the grams of sugar in a regular can of Coke, which is 355 milliliters. Number 3, 2, determine the accuracy of your results using a percent error. Okay, let's review the objectives. We're going to find the density of water, Diet Coke, and regular Coke. How are we going to do that? Well, if you look at your data table, okay, very simply, we're going to eventually get to a data table. And we're going to start with water. Water, you're going to get it from the tap, and be very careful turning the water on in the sinks in the back. They're under a spigot that will produce high pressure for aspirators for AP Chem. So taking the water out of them, just go very slow, okay? And that'd be one way we get the water. That's the way we're going to get the water. So now, we can't pour the water directly on a triple beam balance, obviously. So what you're going to do is you're going to take a container. That container is going to be a beaker. So take a 250 beaker, which is at your table, okay? And you'll take a beaker, which is basically a holding device for liquids, and you're going to mass that beaker right on a scale. That's your container. Okay, and you're going to get, of course, grams. Then you're going to mass the container and the liquid. Well, to get the liquid, you're going to have to measure 100 milliliters. So you're going to take your graduated cylinder, okay, however it looks, and you're going to measure to the 100 mark. Now, I marked out 100.0 because we need to keep 4 sig figs. If you were to put 100, we'd have 1 sig fig, and when we do our densities, all 3 liquids would come out to be 1 gram. So it's very important that you measure out to 100.0 to that level of precision. That's why I reminded you. Please use something called pipettes. They're little plastic bulbs at the end that will top off your level to get as accurate measurement as possible to that, or I should say precise as possible, to that 100.0 line. If you have extra, take some out. All of these materials can be dumped in and out of the sink, no problems. So once you measure 100 milliliters of the liquid, 100.0 milliliters of the water in this case, you're going to be doing the same thing. You're going to put that volume into this beaker, and now you're going to measure the beaker and the volume again right here. Obviously, it's going to be heavier. To get the mass of the liquid, you probably guessed you're going to subtract these two numbers. This is the heavier value, right? And this is the lighter value. So the difference between these two, okay, would give you that value. Volume of the liquid we just have, density, of course, mass over volume. This is an easy one. Look at the units, grams per milliliter. So you have the mass of the liquid that you're going to get here. That, of course, is your mass. The volume, of course, would go here. And look at our value. Make sure that your densities have the appropriate level of significance in terms of sig figs. Okay, so both of these. Now this is a gram per milliliter. Let's go over this conversion. This is an important conversion. Now we're going from grams to liter. Okay, let me talk about this for a second. Let's pretend I'm a princess and we get 1.010 grams per milliliter. Okay, that's 4 sig figs. Now, how can I convert that into grams per liter? Well, I know some people say, wow, it's going to get smaller because we're going to a bigger number with liter, but that would be only if it was liter. This is grams per liter. Watch how I do this. This is very important. It's something I've watched over the years students get wrong. Let me put my number I have, 1.010 grams over a milliliter. We're going to do a converting factor. What do I want to convert to? Well, I want to convert to grams over liter. So my friends in chemistry, this has to be a milliliter up top, right? Now, why am I doing that? Because I want to get rid of milliliters, and I want to get liters. Okay, so what's my converting factor from milliliters to liters? Well, 1 to 1,000, right? Smaller unit, bigger number. So notice how I set that up. Milliliters cancel, and I'm left with that times 1,000. Okay, and of course that answer is going to be 1010 grams per liter. Notice the number got bigger. Look at this was a unit was grams per milliliter. That's how much mass per milliliter. It's only 1, and that makes sense. The density of water should come out to be 1. We've talked about that. But if now I have a liter of water, should I have 1,000 times more grams? Since you're saying in this case that water is about a gram per every milliliter. Divide by means per. So this should be 1,000 times more. People who move the decimal place will get this wrong, okay, by thinking. By using your units, you can figure this out. Intuitively, this makes sense. If I only had 1 cubic centimeter of water, it's about 1 gram. Well, if I have a liter, we learned 2 days ago that a liter is 1,000 cubic centimeters, so it should get bigger by 1,000. A lot more water should be a lot more grams, and that's how you do the conversions. Careful, I have 4 sig figs here. To have 4 sig figs here, and these are just numbers I made up, I would have to put a point there. Okay, so that conversion is very important. This is where I'm looking for correct sig figs. Okay, and you do that for regular Coke, and you do that for Diet Coke, and that's the important pieces of data for objective number 1. All right, now the conclusion questions I'm going to have a separate video on to walk you through, because the second objective is to come up with the amount of grams, okay, per can of Coke. In fact, let's just continue with this and keep this the same video. How am I going to do that? Well, the first step I'm going to say is calculate the mass of a 2-liter bottle of Coke. How am I going to do that? Okay, well, very simply, I'm going to go back to my data, okay, the mass of a 2-liter bottle of Coke. If I go back to my Coke data, now I don't have any Coke data here and you don't have any of them, I'm just showing you how this is done. Okay, take my Coke data and let's just pretend, okay, the Coke density of my Coke data was, I don't know, 115.3 grams per milliliter. I'm just making this off the top of my tall head. Okay, and let's say I convert to grams per liter, which we show the work. That's going to get bigger by 1,000. I made a mistake there. Clearly the density is not that big. That would be a metal. Okay, so this would be 115. So this would be 1.1153, and by the conversion, it'd be by 1,000 times, we're getting this bigger, 1,153 grams per liter, just like I talked about before. So this is a better representative density than I just talked about. So it's 1.15, it's a number made up. And when you do the conversion, just like I did above here for water, that's the value. Now, it's a density, but as I talked about in other things, it's a density what? It's the grams per liter. So this is the mass per liter. What am I asking for here in this question? I'm asking for the mass of a 2-liter bottle of Coke. Well, don't I have the grams per every liter? You should be saying yes, Mr. Grodsky, yes. Well, if I want a 2-liter bottle, what am I going to do with the value that I just had there? If I have the mass per 1 liter, how do I get 2 liters? Well, you times it by 2, silly rabbit. So to answer the first question, all I have to do is take 1,153, this is grams per liter, watch the units, okay? This is grams per liter, and what do they want? They want it per 2 liters, so I'm timesing by 2, all right? And if I times it by 2 liters, watch what happens, party peoples. Liters cancel, and I'm left with what? Just the grams. Now, people say, well, can I use this one? What about 1.153? Sure. If I use 1.153 grams per milliliter using my units, okay, now to get to 2 liters, how many milliliters do I need? I know that 1 liter is 1,000 milliliters, right? So 2 liters is equal to 2,000 milliliters. So my friends in chemistry, if this is per what? Grams per milliliter, okay, then I have to times this by what? Okay, think with that. Well, this is going to be milliliters. This is the grams per million times this by 2,000. Okay, density per liter. And of course, that would give me the same answer. So that's how I'm doing, all right, that question. Now, number 2, very important. Calculate the number of grams of sugar that are contained in a 2-liter bottle of Coke. And this is so very important. If you're tuning out, Mr. Grotzky, I don't want to hear these in class. Put your head up, listen up. This is the crux of the entire lab. We're trying to find grams of sugar. We're using a very important assumption. Okay, what's that assumption? I know what happens when you make an assumption. You make a donkey out of you and me. The assumption is that regular Coke and Diet Coke have the exact same formula of ingredients, same amount of ingredients, except one has sugar and one does not. So we're going to say the difference in these masses is the sugar. That's how we come up. Now, that's an assumption that we're going to test the validity of this lab. So the main crux of this lab, focus people, is that we're going to see if, in fact, we get the right number of grams of sugar from a can of Coke, and we're going to test to see that, hey, does Diet Coke and regular Coke have the same amount of ingredients except for the sugar? So how do you get grams of sugar in a 2-liter Coke bottle? Okay, what you're going to do is you're going to do the same thing here. Whatever mass you got for the Coke, you're going to find for Diet Coke. So you're going to have to find the mass for 2 liters of Diet Coke. And once you have that, okay, this is the mass of 2 liters for Diet Coke. This would be the mass of 2 liters for Coke. All right? Well, if they have the same ingredients except for the sugar, then all you got to do is subtract these two. And when you subtract those two, you're going to get the grams for a 2-liter bottle of Coke. So you're going to subtract these two masses. Okay, and I'll do that over here. So this one minus this one would give me this grams of 2 liters. Okay, very simple premise, but we're going to test that validity. Number 3, how do I get a can of Coke? Because up in front there's a can of Coke that has 355 milliliters, and its known value is written on a nutritional label for carbohydrates. I have the grams of sugar for 2 liters Cokes. How do I par that down for 355? If I know, let's pretend that it was 188 grams of sugar that I found by subtracting the mass of 2-liter bottle of Coke to a 2-liter bottle of Diet Coke, and the difference in the two masses was 188, making the assumption it must be sugar. Guess what I do? Well, this is 188 in 2 liters of Coke, right? All right, and I want how many grams in, well, 0.355 liters, right? This is what we call the proportion. I don't normally do proportions, but that's what we're going to do. This is 188 for 2 liters. How many grams? If you have to use X, people, because the X is always the unknown, solve for your proportion. Crisscross, multiply, and solve for that. You're going to pare that down for 0.355. And of course, you could set that up, what? 2,000 milliliters over 355 milliliters. And of course, that's 188 I have, and solve for X. Same thing, so you're going to pare that down. Okay, last but not least, you're going to go up to see what the known value is on the can, and you're going to do a percent error. That's how we do this lab. Okay, so if you need to review these steps, you have this in your laptops, or your teacher or someone showing you these can replay them. Okay, so number 5, you're just going to give me the reasons why you think in descending order, going from more dense to least dense, why that's the reason. Okay, and then you're done. Okay, and I would think you have enough time to do that. So with your teacher's help and knowing where the Coke and Diet Cokes are, ready, set, go.